I give you a few more examples of the numbers, the important numbers that we use and we come across in the working of non-dimensionalization of equations, and the work that was done by researchers after whose name these numbers were given. And we try to look at some of them, but not all of them, because there is a long list that can be found in books and literature. But the most common number that we come across is that of Reynolds number. And similarly, the other parameters also come, the other numbers also are available. And they are very commonly used in the calculation and also when discussing the fluid flow research problem or in giving of a course and so on. We have mentioned already that the parameters, the scaling parameters that we have to choose should be typical and have some influence on the fluid flow. So if a fish, for example, is moving from left to the right hand side in water or in seawater for that matter, then what are the terms that are occurring there? And when we say the term, we mean the terms that occur in fluid flow motion. For example, we have here, there will be some pressure that is applied or that is working against which the fish will be swimming. If it is moving, it's moving with a certain velocity. Let's say it's v. Its length can be a typical flow situation, and that can be denoted by L. Similarly, the density of the fluid in which it is swimming is rho, and the viscosity or coefficient of viscosity of the fluid in which the fish is swimming is mu, is denoted by mu. And if we divide mu over by density, then this is known to be nu and called as kinematic viscosity. So sometimes we use these terms to mention, to develop these numbers that have become very famous, very useful for discussion of fluid flow and equation of motion. Similarly, the other forces that are occurring, we can see, and obviously they will vary for different flows, the scaling parameters will be different. Gravitational force is there, pressure is there, and so on. So one of the very common terms that we use is Reynolds number. So Reynolds was the first one who used it, and who used it very frequently in his research work, and later on it was found that Reynolds number is the most common number that is used in fluid mechanics for working in research problems that take place and that we come across every day. It is a ratio that represents R. Sometimes it is denoted by R, some authors denote it by RA, and here it is being denoted by RE, but it's taken from Reynolds. And it is the ratio of velocity over L, velocity times L, divided by mu over rho. So if we see velocity into length actually is in a way representing the momentum force that is occurring in the fluid, and mu over rho is representing the kinematic viscosity. You can write it in whatever form you want, but this is the quantity. So this is the ratio kinematic viscosity nu. So RE can also be written as VL over nu, and therefore they are representing the ratios of momentum forces and viscous forces. If the velocity is very high and the viscosity is very low, the Reynolds number will increase and it can be very large. And in fact, when the Reynolds number is in excess of 2000, we say that the flow becomes turbulent. So there is turbulence there. But if the Reynolds number is less than 2000, then we say that it is equal to or equivalent to a laminar flow, and in which we say that the fluid is moving in a smooth manner and in a predictable manner, and it's easier to handle the equations of motion when that kind of flow is taking place. So Reynolds number has a important part in our daily life, and therefore remember this. We need to apply it again and again, and we should appreciate what is it representing. Similarly, Froude number, you can see, is the ratio of velocity over gravity into the length. So in a way, this is ratio of momentum forces again and the gravitational forces. And so this shows how the fluid is behaving, and if the speed is increased, and then of course value of the gravitational force remains the same, but the length scale can change, and therefore the product, it depends whether Froude number is greater than 1. So we need to consider what happens when it is very large. When it is equal to 0, it will be equal to 0 when V is 0, and when it is very small, that is, the fluid flow is moving very slowly, but the gravity is dominant and having an important role. Similarly, the Euler's number, and which is the ratio of pressure and the velocity forces and so on. So these are important things that they generally play a role. In a general unsteady fluid flow problem with a free surface, the scaling parameters include a characteristic length L, as we just show in the earlier photograph, the characteristic velocity V, a characteristic frequency F, and a reference pressure difference P naught minus P infinity. Again, it will have the dimension of the P. So non-dimensionalization of the differential equations of fluid flow produces 4 dimensionless parameters: the Reynolds number, the Froude number, the Stroudsel number, and the Euler number. These are most commonly used in a lot many fluid flow problems and situations. But remember, this is not the end of the list. There is a large list of important dimensionless numbers or parameters that have been named after the researchers who first found them, who discovered them and used them in their work, and their usefulness was determined later on. So we will discuss them later on, again when solving some problems.